Welcome to the HiRSE Seminar Series on Research Software Engineering in Helmholtz and beyond.
Perfect. Thank you, Claire. And thank you again for the fantastic introduction. My name is Sebastian Müller, and we will talk today about when you don't know what to test for, metamorphic testing for research software. This is part of the recently defended PhD thesis, so this is quite fresh indeed. When we're talking about software testing, what we're usually talking about is something that looks like this. So we have our generalized input to our program that we want to test. And if we run our input that we have through our program under test, you might also know this as system under test, method under test, something under test. Out falls an actual output. And the question that we are asking ourselves, is the program actually doing what we want it to do? To answer that question, what we can do is we can take our input, run it through what is known as this oracle, our crystal ball that we need to look into, and generate what is known as this expected output. And usually the check that we're running in the end is, are those two things equal? So when I say oracle, this crystal ball, this is quite fuzzy, and the question immediately becomes, okay, so what are these test oracles? And as a follow-up question, why can they be problematic? Let us start with this very first question: what are test oracles? Well, a test oracle is what determines whether our program's output is indeed correct. The problem that we're facing is, well, when we have our domains, especially science and machine learning, knowing what correct actually means for our program may not be as easy a question to answer. It may not always be known in advance. And this is what makes testing really, really difficult in many situations, particularly in science and research software. So when can we actually consider this oracle to be an easy question to answer? Well, whenever we have simple logic that is deterministic and where the outputs are also generated in a deterministic fashion and are actually known. So what could this be? Well, we could talk about sorting, adding, reversing, all of these very, very standard algorithms that you might know from a standard algorithms lecture. All of those where we can check against this deterministic and known output. So as an example, because this feels quite fuzzy again, what happens if we have this network of a graph here, and we want to run from our starting node A to our target node K, and we run that through our program, which in this case is a shortest path finder, and we're generating this following output. Well, we see as humans immediately, okay, we have these 5 nodes that turn up in this output there. But if we look at our network and assuming that all of the lengths of these edges are the same, well, we can easily find multiple ways of just having 4 nodes. So us as humans can easily come up with this expected output. So us as humans are in fact the oracle, and we can immediately see, hey, this output that we have generated here, that is somehow wrong. Something must be wrong in our program of the shortest path finder. I've already mentioned that we might have an issue with software where we don't actually have either oracles at all, because they are absolutely unpredictable, or without easily attainable oracles, because the software itself becomes unpredictable. And in 2018, Segura et al. have released their paper, Metamorphic Testing, Testing the Untestable. They are actually stating that research software tends to be explorative in nature, and that especially compilers, simulators, and search engines do indeed suffer from this unpredictability of these oracles, and go as far as telling us, hey, these software types are untestable, in brackets, under our normal testing regimes. So if I were to give you this Google search, and we're searching in the image search for software, and out falls a result of 10.29 billion results, what is the oracle? Can we predict what we would expect here? Well, I certainly can't, and I wouldn't expect any of you to also be able to actually predict this result here. So we have a set of very common different strategies of dealing with these test oracles. In the most common case, when we are talking about software testing in general, and we're looking at this typical image of input, program, output, and we have our crystal ball, then we're usually in the regime of this unit testing approach, where we're testing the individual components in isolation. So the program under test that we have seen at the bottom of this image is usually a very small component or module or function of our full-on system that we're testing in isolation. This is the real problem where we might run into these test oracle problems. We can, however, address this in a different way. So we could state, okay, we have a test suite. We just don't know, is this test suite any good? Is this test suite sensitive enough to actually find issues within our code? And this is when we could take a look at mutation testing, where we are injecting small code changes. We are creating so-called mutants, and then are testing our pre-existing testing suite, our test cases that we have generated previously. Okay, can we actually find these code changes through just running our pre-existing test suite? Another approach might be to use what is known as property-based testing, where we're testing general properties of our program that we know are in the program for sure. So the example here would be if you have a topological program, and you have a function that is called fill sinks, and you're filling all of the lowest points so that no pixel in your topological map is lower than any of its neighbors, then the property that you can check for is, hey, the method find sinks should no longer return any result of a single pixel, because, hey, we just filled in all of those sinks. That is the general idea of property-based testing and mutation testing. This talk, however, will focus on metamorphic testing. If there is any interest in giving another talk on mutation testing or property-based testing, please reach out to either myself or Claire, and we could see if we can set up another HiRSE seminar or a talk privately within your research institutes. Now let's actually go and consider what we're talking about when we're talking about this idea of metamorphic testing, where we're inferring the correctness by using relationships between in and outputs. I will come back to that in just a second, but let us briefly recap what we have talked about so far. We have talked about the test oracle problem, and as a key takeaway for all of you is that whenever we're talking about research software or scientific computing, we're often faced with the problem that perfect oracles just don't exist. We have this problem of this explorative research software, of this maybe research software that requires human intervention, where we just can't predict the outcome of a given input. We have also seen that there is different testing strategies that make testing for these projects feasible, just in a different way. And going down on the actual idea, what we are addressing in metamorphic testing, we are using what is known as metamorphic relations. Metamorphic relations are relatively easy to understand on the higher level and become significantly more difficult when we're actually trying to implement them, but they might still be easier than coming up with a full-on oracle that predicts what our program is doing in general. So the idea of metamorphic testing is relatively old. It's from 1998. T.Y. Chen has introduced the approach back in 1998 already. And the general idea is relatively simple to understand. So we're still taking our general input for our program under test, and we're still running it through our program under test to generate our first actual output. But rather than taking the same input and looking into our crystal ball to predict what our program is doing, what we're doing instead is we're taking this input and apply a transformation function, let's call it t, to that input and generate a new input, let's call that I prime. So we now are faced with two inputs, and we are running both of these inputs through the same program under test, and out falls two outputs. And if we can predict how these two outputs are in a relationship with one another, for this given transformation function t on the input side, then we have found what is known as a metamorphic relation, and we can just check on the output side if that metamorphic relation actually holds. This problem of finding these might be difficult for different for different projects, but it might also be relatively simple if you have some templates that we can use for complex input data types. And in my thesis, I have worked with geometrically representable input data. For simplicity, let's just picture an image. And we are taking, in this case, a system that classifies, okay, is there an animal present? And in this case, it should definitely state for the original image, yes, there is an animal present. In fact, it's two dogs. What we can do is we can just apply a couple of templates. In this case, the templates of mirroring, scaling, so zooming in and out of the image, translating, so we're shifting the image up, down, left, and right, or we could just rotate the image. None of these transformations that we're applying changes what we consider the output to be. So we have applied what I coined as invariant transformations. If we can find one of these invariant transformations, and if we apply this invariant transformation with a couple of parameters, what we would expect to see is something like this. So for all of these applied transformations, the exact error that we are finding, our relative error that we're finding for each, should be exactly on the zero line. In my thesis, I had set a 0.05 relative error threshold. So if the error does not go above this 5% of relative error, then I had classified the software as stable under this transformation. So we actually applied all of these transformations in multiple different fields. And for today, I have brought one example, namely neuroscience, where the neuroscientists had CT images, slices of CT images of brain scans of humans, and were trying to predict the actual brain age of those patients that they had these CT images from. And when we had indeed applied the transformations, here we're looking at rotation transformations, what we saw was nothing like what we wanted to see. If you recall, what we wanted to see is we wanted to see exactly zero change in the error bars, because the domain scientists had told us, okay, rotation should be an invariant transformation for our brain age predictor. But what we're seeing is that the further away we're going from the origin, so here's half a degree of rotation, 1 degree of rotation, and so on for the 3 different axes, um, the further away we are going from our original rotation angle, the more of an error it actually creates. So in this case, for the axial in the 90 degrees, so instead of going upright, we had flipped that to the side. We had, on average, nearly 10% relative error. And that was something that was entirely not expected by the domain scientists. And if we're actually applying different transformations, in this case, another translation transformation, we saw something that up until today, the domain scientists have not had a chance, excuse me, had not had a chance of actually explaining this behavior. If we are just translating in the sagittal plane by half a millimeter, we are seeing a significant outlier, both in the positive but also in the negative direction, that the domain scientists neither expected nor have yet explained. So we can actually see, when we are using these invariant transformations, or what the domain scientists consider to be invariant transformations for their program under test, the programs themselves might actually behave differently from what the domain scientists are expecting. So, what can we actually do with this approach? And why should you, as RSEs, indeed care about this approach? When we're talking about metamorphic testing, we are talking about a practical solution that sidesteps this oracle problem, that sidesteps this problem for software that particularly lacks this gold standard test data, or that lacks this idea of a attainable oracle. What we are not doing with metamorphic testing is we are not verifying correctness. What we are doing instead is we are detecting inconsistencies. We cannot, with metamorphic testing, locate, okay, where actually is the bug. We can only detect, okay, here we have an inconsistency, something that should behave differently is now behaving in this way. And we have, with this approach, in 4 different evaluation examples, I've only brought the one example that you have seen already, we have helped detect issues in published scientific pipelines. So we've talked about this brain age predictor, but we've also applied it to a DFT, density functional theory code from the material sciences. We have also applied this to ParticleSec3D, which is a environmental and geoscience tool that segregates material samples. And we have also applied it to Polarity Jam, which is in the biomedical imaging community, a tool that is used to segregate cells from just biomedical imaging data. So we have, in all cases, found issues that were unexpected by the domain scientists that had originally published their software. And in one case, we have also found, this was the DFT code of the material sciences, that against what the domain experts had originally anticipated, 2 of the 4 transformations that were supposed to be invariant were actually unsafe transformations. So what we have seen is that it can help us understand inconsistencies in the program behavior and inconsistency between the understanding of what the program is supposed to do and what the domain scientists actually think this program is actually doing. The cool thing about metamorphic testing is that we can actually integrate this idea into existing testing workflows, such as PyTest or our CI/CD pipelines, or whatever testing framework you might have. We just need to restructure our assert statement a tiny bit. Now, you might ask yourself, okay, that's all nice and very fine, but how do I actually get to these metamorphic relations that you're going on and on about? The first and very, very common source for metamorphic relations is domain knowledge by the domain experts, where you're having this inherent knowledge of the domain experts of existing invariants that should hold true no matter how you apply this transformation. Or you have expected behaviors that the domain knowledge can provide. You might have numerical properties. So in my thesis, I've talked about scaling and the mirror symmetries. But you could also go into noise tolerance, or if you're thinking about, for example, self-driving cars, if you are working on the steering angle prediction and you're just putting over the images that are coming in some slight fog, then it shouldn't change the steering angle prediction. Now, if there was something like rain or snowfall, as long as it doesn't stick to the road, the steering angle shouldn't change. But if it's actually sticking to the road, then you might actually need to see some changes. You could also go into regular data manipulation techniques such as shuffling or domain-specific augmentations. Or you could, if you're back in the material sciences, for example, use some physical laws or constraints that you know must be present to actually have a physical system under test. So if we're recalling this idea of how we're doing metamorphic testing, and I'm already excusing the next slide. I'm very sorry. I'm going to bombard you with a bit of maths. But if you just keep this image in mind while we're looking at the maths, you will also be fine. Because what we're doing now is, let us talk about this formal definition of how this metamorphic relation can actually look like. And we have our program under test, and we have this transformation of one valid input to another. So if we're going back to this previous slide, we have one transformation function that transforms our input, our original valid input, into another valid input. Then we have fulfilled this first real bullet point, and we are defining, okay, our program under test applied to this input will generate an associate output that lives within the set of all possible outputs. And we are also considering 2 more things that are not on the previous slide. We also could consider an output transformation, so something that transforms one output into another. And we need to consider, okay, how do we actually compare these 2 outputs, O and O prime, to each other? So then we are left with this three tuple of a input transformation, an output transformation, and our comparator. And we are saying, okay, this thing here on the backside, our transformed input, if we're running that through our program under test, should be, if we're comparing this with this relatively freely choosable comparator, it should be this comparator should hold true if we compare this to our transformed output of the original input. This might sound very confusing for a lot of you, so let me go back and give you a basic example. Let us consider we are required to write a calculator and test this calculator's newly implemented sign function. Then, from our original math classes back in high school, we might know that, hey, whenever we are taking our input and we're adding 2π to that input, we know that the output of the sine function should be the same, because the sine function, as we all know, is this periodic function. So what we're testing is this invariance of this transformation, that when sine of x, where we're taking this as our original output, we are looking that sine of x plus 2π is the same as sine of x. So we have found one metamorphic relation in a maths based system. But we could also say, and this is where the output transformation comes in, that, hey, if we're just adding a single pi, not 2π, but a single pi to our original input, then we know through our maths knowledge from high school that our output should be the negative of whatever we have generated. So what we're testing is the equality between sinus of x plus pi and the original value sinus of x, but we're negating that. So what we have seen, okay, we can actually change, if we're going back to this slide, we can both change this transformation in the front, but we can also change on the output side. And I'm hoping that you'll just believe me if we can, if I say, okay, we can also change this comparator here. An example would be if we have a rain or a fluid prediction system for a certain topography, and we're adding more water on the top of the mountain, then at least in the valley, we would expect no less water. So we have this monotony where we are comparing with greater or equals than as this comparator. So we have seen that we have these three places where we can play around and actually generate new metamorphic relations. Why am I going on and on and on about these three tuples? Because also in my thesis, I have formulated the lemma that you see on the slide. And the important bit is that whenever we have an invariant transformation, let's call it T of I, then we will always, always, always have a metamorphic relation of the form. We are using this invariant transformation. Our output transformation is the identity, so we're not changing anything, and the comparator is the equality. So whenever you know that you have an invariant transformation, a transformation that if we apply that to our input of our program, then you will also already know, okay, we do have a metamorphic relation in our program that we can test for. And this might be an easier way of testing your software rather than applying this idea of this oracle function that we need to look at in this crystal ball. So I've talked for about half an hour now, and I'm coming already to the end of this talk. So what are the key takeaways for you as RSEs? Well, metamorphic testing is a lightweight and a domain adaptable way of increasing your confidence in what your programs are doing. It doesn't really replace the validation, but it might help you catch implementation and integration errors by uncovering inconsistent behaviors in your programs. Something where you might not have a metamorphic relation that holds anymore is an indication that maybe something is going wrong, or that your understanding of the program is not as the thing that you have indeed implemented. It is especially valuable if you don't have these reference outputs, this crystal ball, or if those are unreliable because you might use something like randomness in your program. If you have any non-determinism in there, then your oracles are really, really difficult. And we have seen, or I have told you that when we're applying these small transformations in our case studies in real world scientific publications, we can indeed expose serious flaws or serious misunderstandings of what these software pieces are actually doing. And with that, I'm coming to my last slide, the summary of what we're talking about when we're talking about metamorphic testing. And I would be absolutely happy if all that you're keeping from this talk is this idea of this scent glass clock idea of how metamorphic testing is actually working, that when we're taking our input and transforming that, running both those inputs through our program under test, and out fall these two outputs that we can then check with these metamorphic relations, if these metamorphic relations are indeed present in our outputs. And I would absolutely love if you also remember that whenever you have an invariant transformation in your program, it will always, always, always lead to an equality metamorphic relation. And with that, I would ask for any questions.
Thank you for watching our seminar. Please check out the slides on Zenodo linked below and see you next time.